Hello, I'm Forrest Hoffman from Oak Ridge National Laboratory, and I'm going to present lecture 5.3, an overview of benchmark analysis. First, we want to ask, what is benchmark analysis? Well, it's similar to validation, which is a common approach for model evaluation that involves comparison of one. However, benchmark analysis is a more holistic and comprehensive procedure for measuring the scientific performance of models in comparison with a set of defined standards and reference data. A useful benchmarking framework includes the process of defining targeted aspects of model performance to be evaluated, testing model performance in comparison with a set of reference data, measuring model performance skill through quantitative metrics, and using model performance results to inform future model improvements. Reference data is typically a compiled set of measurements, observational data sets, or observationally constrained synthetic or model data. A framework for benchmarking land models is shown in the figure at left, where the model aspects to be evaluated are identified. These may be processes such as biophysics, hydrology, biogeochemistry, vegetation dynamics, or individual parameters, state variables, rate variables, fluxes, responses, feedbacks, etc. And then in the next box, we define benchmarks. So that means identifying appropriate observations for what we want to measure, what we want to compare, experimental results, defining a simulation protocol, data model products, and relationships and patterns. And these need to be at the right spatial and temporal scales for comparison with the model based on what we expect the model to do. And in the third box, we develop matrices of performance skills or tables where we establish a priori thresholds and have a scoring system that considers weights for different processes and data sets. And that helps us determine the model's acceptability, ranking, and strengths and weaknesses. This information is then provided and fed into the process of model improvement, where we may identify missing model structures or errors in model parameters or poor initial conditions or problems with input variables. Once these model improvements are made, then we circle back around and perform the simulations and evaluate again. Based on this land model comparison project, our group developed a land model benchmarking package for the International Land Model Benchmarking Activity, and we call that package ILAM. Before talking about that, let's start off with defining a benchmark. So a benchmark in our case is a quantitative test of model performance or model function that we achieve through comparison of model output with observational data. Acceptable performance on a benchmark is a necessary but not sufficient condition for a fully functioning model. An example of such a benchmark is shown in the figure in the upper right, where we have the detrended CO2 mixing ratio in the atmosphere at Sand Island Midway by month. So over that time period, you see the observations are in have a higher amplitude than the two model results that we're showing over plotted, and the phasing of those two model results is slightly different as well. So this allows us to score the performance and the amplitude and the phase of models capturing this interannual variability of CO2. That's a direct metric. And then functional relationship benchmarks offer tests of model responses to forcings and yield insights into ecosystem processes themselves. So in the figure on the bottom right, we see net primary production shown as a histogram plotted against precipitation. And so we have this information from observations as well as from these two model results. And what we want to see is if the shape of this curve from the model results matches the shape that we see in the observations. If it does, then no matter the spatial distribution biases in the model, at least we're capturing in the ecosystem models continue to increase their net primary production, even as the observations have sort of rolled over in NPP at very high precipitation rates. Now, effective benchmarks must draw on a broad set of independent observations to best evaluate model performance at multiple scales. Why do we want to benchmark models anyway? Well, we want to quantify and reduce uncertainties in carbon cycle feedbacks to help us improve projections of future climate change. We want to quantitatively diagnose the impacts of our own model development on hydrological and carbon cycle process representations and their interactions with the climate system. We want to guide synthesis efforts such as the Intergovernmental Panel on Climate Change by determining which models are broadly consistent with available observations over the contemporary period. We want to increase the scrutiny of key data sets that are commonly used for model evaluation and identify gaps in existing observations needed to inform future model development. We also wish to accelerate the delivery of new measurement data sets for rapid and widespread use and model assessment by the modeling community. These activities are all part of a broader model data experiment process in which we, for instance, here identify key knowledge gaps and then conduct process research and site characterization and experimental design, either in the lab or the field, in order to address those knowledge gaps. We make field measurements and conduct manipulative experiments. We take that data and synthesize and scale and integrate it to inform model development, employing a modular design that we then benchmark those simulation results to inform us about whether we have addressed knowledge gaps or created new knowledge gaps as a result of that investigation. So this cycle continues on in this clockwise direction primarily. Now back to ILAM. So ILAM was originally a community activity designed to develop internationally accepted benchmarks for land model performance, drawing upon the collective expertise of the global community. And the idea was that we wanted to promote the use of these benchmarks for modeling and comparison. We also wanted to strengthen linkages between the experimental remote sensing and modeling communities and support the design and development of new open source benchmarking tools. So ILAM has now become a community of people, global group of modelers and scientists who are enthusiastic about benchmarking, as well as a set of curated data sets that provide the references and comparisons with observations, a set of methods or a library of techniques for benchmarking land models with those data sets, and then a set of software, an extensible open source, fully interactive Python package for evaluating multiple models. And then the results. So the results of running ILAM against a standard set of existing models to provide an easy to use catalog of model data comparisons. Now ILAM includes a number of variables and data sets for those variables against which it compares model results. And these fall in the categories of biogeochemistry and hydrology, energy, and forcing. So for biogeochemistry, we, for instance, have a number of data sets with different spatial domains for biomass. We have a burned area data product, CO2, gross primary production, leaf area index, global net ecosystem carbon balance, net ecosystem exchange, ecosystem respiration, and soil carbon. And so for every one of these variables, we have a data set. The data sets that we have are listed in parentheses. And these are the curated and accepted data sets that are available in the package, and users are free to add additional data sets as needed. But this provides a framework for easily distributing those new data sets and providing the methods that users can use to compare their models. Thus, metrics and scores. So it first generates a top-level portrait plot of relative model scores. And then for every variable and data set that we showed on the previous slide, ILAM can automatically produce tables of metrics and metric scores, and that includes the period mean of the benchmark or reference data, as well as each of the models, a bias or a difference between the model and the observational benchmark, and then a bias score that becomes associated with that bias. It calculates a root mean square error and then scores that RMSE. It generates a phase shift metric and scores the phase shift, and an interannual coefficient of variation and scores that as an interannual variability, and then looks at the spatial distribution and does a correlation. So we have a spatial distribution score. And then the overall model score for a given data set and variable is computed as the average of all of these individual scores while weighting the RMSE score twice. In addition, ILAM produces graphical diagnostics, including spatial contour maps, time series line plots, and spatial Taylor diagrams. Similar tables in graphical diagnostics are generated for functional relationships in addition to individual variables themselves. So this is an example of a portrait plot for ILAM assessing several generations of the community land model. And you can see those biogeochemistry variables in green under the ecosystem and carbon cycle label, hydrology variables in blue, and the radiation and energy variables in pink. For each of the models, we see there's a column for CLM4, CLM 4.5, and CLM 5. And we can see that by looking at the relative scale over on the left-hand side, that model performance improved overall between CLM4 and 4.5, and then again between CLM 4.5 and CLM 5. So this relative scoring display allows us to easily see where the models have made the largest improvement and maybe where new issues have arisen or problems and differences are shown in the new version. So as we develop the model, as easily find the problem if in the process of improving one variable, we've actually degraded performance on another. ILAM produces graphical diagnostics as a part of benchmarking. In the upper left-hand corner, we see the benchmark mean from the data for the gross primary productivity, this annual mean GPP from the GBAF data set. In the second column on the top row, we have the model mean. So from the CLM5 model, this is the same GPP over the same time period that we would compare with the benchmark at the left. And we can compute the difference, which is the bias, which is that third column, the top row. We can score that bias overall using a function for computing scores. We can calculate an RMSE difference between the model and the benchmark and score the RMSE. We can look at the maximum month. So looking at the phasing of GPP globally, we can find the maximum month from the benchmark and then the maximum month from the model and look at the difference between those two in order to gauge the performance of the model. This diagnostic at the top is a spatial Taylor diagram, and you can see points for each of the three models there around a 0.9 correlation. But the one closest to the 1.0, that CLM 4.5, is probably slightly better than the other two models for the spatial correlation. And then at the bottom, we can look at the spatially integrated regional mean. And so the whole time series is plotted from the model and the observations overplotted on each other. We can break out just the annual cycle, look at the monthly anomaly, and then the annual cycle with all three models overplotted. For variable to variable comparisons, we generally have something like a heat map. So for gross primary productivity versus precipitation, the observations give us a figure like in the upper left-hand corner. From the model from CESM2, we get a heat map that looks like the upper right-hand corner, and we can difference these two in order to get the figure at the bottom left. And we can see that the majority of the cells in the red and mostly the red colors and the blue colors, those cells represent places where the model is doing the least well. So between 0 and 2 millimeters per day at relatively low productivity. So this informs us about where to go. Then we've plotted this variable to variable comparison as a histogram globally so that we can see how well the model lines up with the shape of the curve of GPP versus precipitation that we get from observations. Now, land model performance depends strongly on the forcing variables that feed the model. So this comparison of CLM4, 4.5, and 5 we're forced with two different sets of forcing, and we can see that some model versions may perform equally well or within the uncertainty of the observations with one set of forcing, whereas another model may perform equally well with a different set of forcing. So it's important to keep in mind that how the models are forced and set up is as important as what the models do. It's also important to consider uncertainty in the observations themselves. So a few observational data sets actually provide complete characterized uncertainty. However, there are many ways to sort of attack this problem. One is to come up with some expert derived can derive uncertainties by combining multiple data sets and looking at the statistical properties of the resulting mean. ILAM can use any of these methods for including uncertainty in its model data comparisons. Now, we've developed a similar package called IOMB, or the International Ocean Model Benchmarking Package, in order to evaluate ocean biogeochemistry in much the same way as we're doing for the land. And these can be combined to give a more comprehensive view of model intercomparisons. So this figure shows on the upper half a subsection of land model benchmarking results for CMIP5 models versus CMIP6 models, and in the bottom half the same for ocean model benchmarking. What we can see overall, just by looking at the land model results in the suite of models, generally has more blue in it than the CMIP5 set of models, right? So the scores tend to be higher. And that indicates that the models have overall improved between CMIP5 generation and the CMIP6 generation. Now, the multi-model mean, the last two columns in the figure, show that the multi-model mean outperforms in a single model for its suite, and the best model is this multi-model mean CMIP6 model, as it gets the highest relative score values for many of the variables, but not all. If we were to drill down on gross primary productivity from this CMIP5, CMIP6 comparison, we would get a table that looks like this, where we can look at the period mean, including from the benchmark, and what the bias, RMSE, and phase shift are, and then what the scores are computed from all of those quantities. And we can, for instance, look at CESM1 BGC, that row, versus the CESM2 row, and recognize that the scores have overall improved in CESM2 versus those same scores in CESM1 BGC. And likewise, for most of the other models, we see more green in the newer generation of that model. So in conclusion, I would say that model benchmarking is becoming increasingly important as model complexity increases. We need better ways of understanding uh, the performance of the model as it's becoming more and more complex. Systematic model benchmarking, like that done with this benchmarking approach using ILAM, is useful for verification during model development to confirm that new model code improves the performance in the targeted area without degrading performance in another area, and also useful for validation when comparing the performance of one model or model version to observations or to other models or other model versions. The ILAM package employs a suite of in situ, remote sensing, and reanalysis data sets to comprehensively evaluate and score land model performance. Again, ILAM is an open source Python package that runs in parallel, and it's been adopted by various international modeling centers to evaluate their land model. Of course, the usefulness of any benchmarking package, including ILAM, depends on the quality of the incorporated observational data, the characterization of uncertainty of those data sets, and the selection of the most relevant metrics for characterizing the particular application. So that's the end of the lecture. I want to thank you, and I include 2 pages of references here that provide further reading to complement that from your text. Thank you very much.